All right. Good morning. Um, sorry, a little bit late today. Um, we'll survive. Uh, so just as a little bit of review now, um, I want to kind of leave confidence intervals in the dust for just a little bit. But we did introduce confidence intervals, and we did do an example, and today we're introducing hypothesis testing. And so just for a little bit of review, we did, well, maybe not review, but as a reminder, maybe, we did confidence intervals or a confidence interval for one sample proportion. Now, a confidence interval, right, we use them to find a plausible range for our parameter that we're trying to capture. In the one sample proportion case, we're trying to capture the population proportion, right? And so then at some confidence level, we're able to build a confidence interval and find a range of plausible values, right? That with some level of confidence captures the population proportion in this case. Yeah. And so let's see, this is section 5.3. Yeah. And I know, kind of disappointing. That's all I'm going to say about confidence intervals. We can talk about, well, just as a quick recap, on our formula sheet, right, we have our sample proportion, we have a critical value Z star, which we talked about finding, and we'll see that table again. We used a new table, the T table, to find it because it's a little bit easier than using the Z table. And then we have the square root of p hat q hat over n, which is the standard error of p hat. Okay. So here, this chunk is the standard error of p hat, and then this chunk, that whole plus minus, that buffer area, is the margin of error. Yeah. Now, just as a side note, if you've already started on Lab 7, then you can do the first question because it's a confidence interval, but question 2 is hypothesis testing. So if that looked terrible to you when you opened it, then that's totally fine. We're going to introduce it today. So you've got time, but that's the curse of the Monday lab when we have a Tuesday, Thursday class. It makes no sense. I don't know who decided that, but it definitely wasn't me. And so just as a quick note, a note about Lab 7, question 1 is a confidence interval, whereas question 2 is a hypothesis test, which we haven't done yet. Okay. But I make these due dates way out in advance for that reason, because we have early labs and it gets a little bit bungled. So that's why I'll highlight this, which is what we're doing today. Okay. So there, let me just fix something here. I like put my chat in a weird spot here. There. Okay. So now, hypothesis testing is the meat and potatoes of this entire course. It's why we have to take this course. It's a formal testing approach for significance. Okay, so just in general, if you're reading an article and it says that these two things were significantly different from each other, then they have done the hypothesis test and they've had to use all these formal methods. Now, I don't, it's funny because sometimes I like the slides and sometimes I don't like the slides. And this term, I don't like how they're not working for me. So, um, I'm going to be adding a bunch of pages between the title page. I'm going to keep the slides in there because they do introduce um, kind of another problem, um, and that we'll kind of skim through. But in general, what I want to do to start here is just introduce hypothesis testing. Okay, and so hypothesis testing, let's start there, is when we want to establish significance. When we want to um, establish significance formally. Okay. What I mean by that is product A is significantly better than product B, right? By some measurement. Okay. And so we're going to start a little bit lower than that because we'll just have one sample proportion, but we'll talk about what that means. But for example, um, being able to say product A is significantly better than product B, for example. All right. This significantly requires many, many formal steps of hypothesis testing. Okay. And so this is what makes us require hypothesis testing, which from here on out, I'm going to abbreviate HT because otherwise it's too long to write all the time. Okay, so in our scenario where we're starting, we have collected one sample and we have a sample proportion. So for us, for one sample proportion questions, which is where we're starting and building all our concepts from. Okay, so for one sample proportion questions, we've collected one sample, obviously. We have collected one sample, oops, and calculated a sample proportion. And calculated a sample proportion p hat. Now, that's all good. We use the confidence interval to be able to say, okay, I understand that my sample proportion is not necessarily the exact same as a population proportion, but I'm assuming that it's, within a range. And so then I'm able to build these bounds and I'm able to say I'm 95% confident that I've captured this population proportion. So another thing that we could do is we could say, okay, what if I want to compare this p hat? What if I want to compare this sample proportion to some value, right? So kind of going back to this example, what if I want to compare my sample proportion and say that it's significantly better or different or whatever than some number, right? In this case, we only have one sample instead of two samples. And so now what we're going to be doing in hypothesis testing, what we're going to be doing is we compare p hat. So we want to know if p hat, so this sample proportion that I've collected, right, is significantly different from From what? From a hypothesized proportion, right? I've got this idea of what I think my population proportion might be. And so then I can say, okay, what if I've collected the sample proportion? How different is it from this hypothesized proportion? So we want to know if p hat is significantly different from a hypothesized proportion. Now, how we're going to denote this is we introduce a new p and we use a little subscript 0, a little subscript naught, okay? So this hypothesized proportion denoted by p subscript 0. So it's a lowercase p and a subscript 0, and p naught is pronounced and I think it's N-O not or null. Oops. So it's a 0. Oy. Can't write at all today. There. And I guess there. Okay, so it's going to be a p subscript 0, a p naught, or a p null, and the reason for that is going to be clear in just a moment, but for now we're just comparing our sample proportion to some hypothesized proportion, and then we'll be able to say, okay, these two things are significantly different. What would that mean? If our p hat was significantly different from p naught, then it means that our sample proportion is unlikely to have come from a population that's centered on p0, right? And so in terms of our normal distribution, now we're saying, okay, this thing is going to be centered on p naught. Okay? If I find a p hat, let's say I find a p hat, and maybe I should use some other color. What if I find a p hat here? It's hard to say, but that's kind of within the realm of reason. You know, you're expecting your p hat to be moving around within a certain range, right? Within 2 standard errors is typically what we say. And then, whereas what if I find a p hat up here? Looking at the curve and where I expect my p hats to be, I expect my p hats to be centered around p0, because if that's where the center actually is, then that's cool. So then that's cool. That's not teaching language, is it? So then we say, fine, that's allowed. Haha, there we go. And so how can I quantify how likely or unlikely seeing each of these p hats is? So these are my two scenarios, right? And maybe to emphasize things, maybe I'll bump it even closer, right? So I've got this option for a sample proportion. Here I would say this p hat is not significantly different from p naught, right? It's falling in this area where I'm expecting my values to be. And then intuitively, what do we say, or what do we see here? When I say, okay, I found a p hat that's way out here, right? It's so far away from p0, then your gut reaction would probably be, I okay, that could happen. It could, right? But it's unlikely that it came from a population centered on p0. It's more likely that it came from a population centered on something else, potentially something larger than p0, right? And so maybe let's call this p hat 1 and p hat 2, right? Just so we can call them different things. So consider p hat 1, oops, p hat 1, right? It's very close to p0, right? It is close to p0, or P naught. Okay. Which means that it's not necessarily significantly different from P zero, right? Which means P1 hat is not significantly different from P0, right? I'm expecting values of P hat to fall around P0, right? Now, if we consider P hat 2, oops, it's quite far away from P naught, right? So although it's possible that P hat 2 came from a population centered on P naught, it's unlikely, right? And so although P hat 2 um, uh, could come from, oops, a population centered on P0, oops, centered on P0, P naught, it's unlikely, right? It's more likely that it came from a population centered on something else. It is more likely it came from a population centered on some other proportion. Okay. That page here. Okay. How can I quantify these likelihoods? Right, so what could I do to say, well, the probability of seeing something as extreme or more extreme than P1 hat is very large, right? Meaning that it's pressed up close to the center. Okay? Whereas here in P hat 2, how can I quantify? Well, the probability of seeing something more extreme, so as extreme or more extreme than this, is going to be very, very small. Okay. And so that's going to be the root of hypothesis testing, is saying, okay, sure, I saw this, but the probability of seeing this P hat 2, if the population is in fact centered on P0, is very, very small. And so for that reason, although I could be wrong, right, and we'll talk about what it means to be wrong, I could be wrong, but it's more likely that it came from a different population. Okay, and so to quantify, oops, how likely a P hat, how likely a P hat is to have come from a population, oops, from a population centered on P0, population centered on P naught, we calculate the probability of seeing something as extreme or more extreme than what we saw. We calculate the probability of seeing something as extreme or more extreme than what we saw. Okay. This is called a p-value, which I know is confusing because so far we've got p's, we've got p-hats, we've got p-naughts, and then all of a sudden we're introducing a p-value. But why? Why is it a p-value? Because it's a probability, right? Areas under the curves are probabilities, and so now in general we call this a p-value. Okay, so here this is called a p-value. Okay. So we calculate the probability, right? And that's why it's a p-value of seeing something as extreme or more extreme than what we saw. I'll reintroduce it again, and I'm going to really harp on what this is because it's a difficult concept, right? But just if you think about, right, this scenario, these two different scenarios here, this area, right, this probability is very large. And so I'm fine, I'm okay with saying that it probably came from a population centered on p0. Now here, right, in p hat 2, I'm saying, okay, the probability of seeing something even more extreme than this is very small, meaning that it's unlikely that it came from this population centered on p0. And so that's going to be the root of hypothesis testing. Okay. And so I just want to introduce that concept right away, that we are going to be working towards probabilities, areas under the curve, which we're familiar with, which is nice, right? But now we're really applying it as the probability of a hypothesis. Okay, so all right, I think we're ready. Now, I'm gonna warn you that hypothesis testing, there's a lot of steps, and there are steps that I want you to follow every time. And so I'm going to outline those steps, but within each step there are caveats and there are rules. And so I approach it as a very kind of complicated game, okay? But once you've learned the rules of this game, right? Then you apply those same rules across to any of the question types, right? So we're going to spend a lot of time here developing these rules, and then they'll apply to all the other scenarios, and so that's really nice. But what that means is it can get a little overwhelming in the beginning when I introduce all these rules, but just know that once you have these under control, then you're off to the races. You can do any sort of hypothesis testing. Okay? All right. So what are the rules? Well, first thing, I break it up into 4 steps, I guess kind of 5 steps. But for you guys, because you're online, I'm not too concerned about checking the conditions. Just like confidence intervals, we have to check conditions. So it'll be less of an emphasis, but I break it down into 4 main steps. Okay. And so I'll do a run through. I don't know, and I don't think I'm alone in this, but how I learn best is to have the overview and then go back in and fill in the pieces. Okay. And so that's how I want to approach this. And that's why I always found it's so much easier to study for final exams than tests, because you don't know what's coming, but final exams, you have everything, right? And you know what you need to learn, right? And so that's kind of how I'm going to approach this, I guess. And so hypothesis testing, um, will always follow these steps. And maybe I'll say these 4 steps. I'll throw that in. Step number 1, and you don't have to list the steps. I just find that it's helpful to have kind of a guide. Okay. And so step number one is going to be state the hypotheses. Okay. You have to state what are you testing, right? And so one of the key things that I want to go back to our previous this kind of example here, if we had to dig deep, what was one of the assumptions? Our initial assumption was, fine, I assume that that this population is centered on P naught, right? And so we have to assume that there's no difference between these two things. Okay. And so that becomes our null hypothesis. And that's why we use a P naught, right? Or a P0 is because it's from the zero hypothesis, the no change hypothesis. Okay. And so usually what we want to show, right, or are hoping to show is that, well, maybe my sample proportion provides me enough evidence to say that that's unlikely that it came from this null hypothesized proportion, right? It's more likely that it came from somewhere else, right? And so that would be my alternative hypothesis. Okay. And so I'm going to have two hypotheses. The first one is always one of no change, right? So these two things are the same until I have proof otherwise. Okay. So the hypotheses are going to look like this. H naught. So this is pronounced H, and I can't remember. I'm racking my brain if it's N-A-U-G-H-T or N-O-U. A or O? I'm getting a nod. I don't know. That does. Maybe I'll just make my O look like kind of like an A. Just cover my bases, right? And so this is my null hypothesis, right? This is my null hypothesis. And this has to be a statement of no change. A statement of no change. Okay. What does that look like? Okay. Well, it's a statement. Let's start with that. Kind of a big one. And a pet peeve of mine, too. The null hypothesis is a statement. And so I follow it with just a colon. Here's my statement. A lot of people want to throw an equal sign in there, but that's not the case. It's just a statement. Okay. All right. What do I want to make statements about? Well, in our example, we only have a one sample proportion scenario. And so what do I want to make statements about? I want to make statements about my population proportion, P. All right. I know everything about my sample. I can tell you if it's different from some value, right? That's not what I'm interested in. My sample is representative of the population that I want to talk about, right? And so here, right, I want to hypothesize about the population proportion P. It's a statement of no change, which for us is going to mean that you always have an equal sign in your null hypothesis. Now, if you keep going in stats, they're going to want to say, oh, yeah, you can make it a little bit fancier, but it'll always include the equality, right? No change, equality. And so here, you're always going to have the equal sign. Okay. So I'm going to just map this to the equal sign, just as a reminder. Okay. And what do we want to compare this thing to? I want to compare it to that value that I'm interested in, right? Does my sample provide me evidence that it came from a population centered on P naught? Oh, that was a big P. P naught. Huh? So for a one sample proportion type question, this is always going to be your null hypothesis. The tricky part is that this is going to be replaced by some number, right? And so here, where P naught is a value from the question, right? Is it significantly more than 60%? Is it significantly less than 30%? Right? And so so that P naught is going to be some value, some number from the question, okay, that we want to compare our sample proportion to. And maybe I'll add that. Where P naught is a value from the question that we want to compare the sample proportion to. All right. So now our alternative hypothesis, I use HA for alternative. A lot of books, I think especially if you're in biology, I think they use H1. And so that makes sense, 0 and 1, sure, whatever. But this is the alternative hypothesis, which is usually what we're trying to prove. Not always the case, but usually. Usually what we want to prove. What's this alternative hypothesis going to look like? Well, it's another statement, right? If we think about it, would it make sense to make a statement about anything but P? No, because we said, well, I want to know how P compares to this P naught. I suspect that it's different from P naught, right? And so then, well, my alternative hypothesis is going to be that. And so I'm going to say P is not equal to P naught. The only thing that changes is this equality, or inequality, I should say. Okay, and so in HA, the only thing that changes, right? The only thing that changes is the inequality. In fact, there are 3 options, right? And so there are 3 options. If I want to show that P is less than P naught, right, then what would I have to have in my sample? So let's just say that P naught is 0.5, right? Just 0.5, which is kind of a common one anyways. Why? Why does 0.5 feel like a good place to start? Well, anything larger than 0.5 is a majority, right? So especially if you're talking about voting and things like that, then you would be interested in how your sample proportion compares to 0.5. Is it more than 0.5 is usually what we want to know. Okay, and so in general, what we're going to have is P maybe is less than P naught, in order to prove that, my sample proportion should probably be less than P naught. Otherwise, it's really hard to use zero 0.8 to prove that it's less than 0.5, for example, right? It just doesn't work. You could use 0.4 to prove that it's significantly less than 0.5. They're different, right? But is it significantly less, right? How far into the tail is it? And so here, right, if we want to know if P is less than P naught, then in terms of your distribution, it's going to be centered on P naught in all of these cases, right? We have to assume that it's centered on P naught until we have proof otherwise. And if I want to prove that P is less than P naught, then I hope that my my P hat is somewhere less than P naught, right? Otherwise, it's hard to go against that. Yeah. And if I want it to be less than, then what I would do is I would say, okay, well, yeah, it is. So this P hat is less than P0. I want to know if it's significantly less than P0. So what I do is I need to find the area in the lower tail. Yeah? The probability of something as extreme or more extreme. Yeah? And the second option is, what if I want to show that P is greater than P naught? Well, again, I better hope that my P hat, my sample proportion, starts off greater than P0. Otherwise, I'm kind of hooped. It's hard to use a value that's smaller than the value that I'm interested in to prove that it's greater than it. It just doesn't work. Kind of, I made this first one a little big, and now I have to shrink it down. Anyways. So here it's still centered on P0, and I better hope that my P hat maybe is somewhere greater than it. Then the area that I would want is to quantify how different these P naughts and the P hats are from each other is going to be the upper tail. Now you're going to be using software for this, and so we'll use the table, but you can use software if you want. Excel probably. Right, then you need to find the area in the upper tail, which means, well, software Excel only gives you the area to the left, so then you have to use the 1 minus trick, right? That's fine. Most often, we'll just want to know if P is just different from P0. Is this sample proportion significantly different from 0.5? The tricky part here is that your sample proportion is only going to be in one tail, right? But when we want to know if it's different, we say, okay, well, I could replicate something that extreme in the other tail as well. Okay. And so then you have this two-tailed scenario. So my poor curve just gets smaller and smaller. I felt so rich at the beginning there, I guess. P naught. Now let's say that your P hat is down here, right? You quantify, okay, the probability of seeing something that extreme is this, right? This area to the left. And then you say, well, I could have also been concerned if the same thing happened in the upper tail, right? Or vice versa. If your P hat is in the upper tail, you would replicate it in the lower tail, because when you want it to be different from, you don't care which direction it's going in, right? So you use both tails. Okay. And so let me just make this a little bit darker so it's more obvious. Yeah. This is the default. So this is called a two-sided test. Let's see here. This is a one-sided test, one-sided or tailed test. And this is a two-sided or two-tailed test. Told you I'd be going rogue and writing a lot here. So this is the default. The two-sided test is going to be the default. And then if we want to get more specific, we can use one-sided tests. And so here, this is the default. If you're not sure, right, it should be obvious from the question, but if you're ever unsure, then just use a two-sided test. It's better than using the wrong side. Right? And so, okay. All right. Step one feels like a lot of information in step one. I got carried away, I think. I was going to do a quick overview and then I get into the nitty gritty. Sorry about that. But we're getting through it. Okay. So step one, stating your hypotheses. Now, so here, right, we've got our null hypothesis. P came from this population centered on P naught. That's what we have to assume until we potentially have proof otherwise, right? And so then I can say, okay, it's more likely that it came from a population that's not centered on P naught. Notice how we don't talk about where it could be centered. We just say, well, not there. And then we would need to do more work, but that's what it's all about. Now, here, you would check the conditions for the central limit theorem, but I'm going to ignore that step for just a little bit longer. Okay. Because I want to talk about the important things. Okay. So the second step that we're going to do here, and if I gave you enough time to kind of sit back and think about it and just kind of how do I do this, and maybe look at the formula sheet, which I haven't introduced yet, but it's on there. What would you have to do? What would you have to do to find this area? Well, the only way we know how to find this area in the tail is by using z's and z scores and the z table. Yeah. And so that means that the Z is kind of the next logical step, which is exactly the case. In general, we're going to call this a test statistic. Okay. And so here, step two is calculate the test statistic. I'm not saying calculate Z because this test statistic changes depending on what you're doing. Okay? But all the time, this is your next step. Calculate the test statistic. I tend to call this do the test. It just sounds cooler, do the test, right? It's more fun than calculate the test statistic. And so usually I just summarize it as do the test. Okay, this is where our formula sheet comes into play, because for each section or each type of question, we have a test statistic that's given to us. Okay, and so I'm going to bring it in now. Oh, no, thank you. Where is it? Where's that? Keep bouncing it around. Here we go. Okay. So here we're in the one sample proportion section. We've done the confidence interval. Hey, look at this. Isn't this nice? I give you the null hypothesis. That's always going to be your null hypothesis. We already established that. And so the only thing you need to find is the P naught, right? What is that value? Once you have that, you know your null hypothesis. And so then you can kind of figure out your alternative, what the sign change is in the alternative. So that's nice. You've got a good chunk of information here. Now notice that I also give you a Z calculation. Okay, and so here I'm gonna grab this, copy, I'm gonna bring it in here. So doing the test means calculate a Z in this type of question. Now, I just want to look ahead just briefly, right, and show you that, okay, then we move into two sample proportions. There's a lot here. Don't worry about that. We're going to pick it apart, right? But then I calculate a Z. Oh, phew, it's huge. But so don't look. But just focus on the Z, which we know how it works. We know how to find probabilities associated with Z, right? Then, we calculate a chi-squared. It's our first new test statistic, chi-squared. And then if I jump across here, just so I'm not scrolling around so much, we calculate a t. Now those are the, well, we might calculate an f as well, but we'll see if we have time. Those are really the only test statistics that we're gonna work with. Emily, you can't just say that's all when you just introduced a ton of things. Yes, I can. Really, really downplay it. That's all we'll need to be able to do. But we'll get there in due time. Okay. So what does a Z do? Let's break it down that way. Z tells me how many standard deviations, just traditionally, how many standard deviations some observation is from the mean, right? Just in general, that's the Z that we've worked with so far. So it's not that far-fetched to say that, well, what if I want to know how many standard errors, right, P hat is from P naught? That seems like a logical thing to do. Notice that this standard error is different from the standard error in the confidence interval. Okay, and so that's one of the trickiest things in my opinion. This is the standard error for hypothesis testing. Okay, which uses P naught, right? It relies on the hypothesized population, which relies on the hypothesized population. So just slightly different, but from step one, we already established what your P naught is going to be, right? And so here's your step one. And so then you have your P naught, you have your sample proportion, you have your P naught, you have your Q naught because that's 1 minus P naught, right? And so here, recall Q naught is 1 minus P naught. And you're welcome to use 1 minus P naught if you want, but I am lazy. Besides the P naughts and the Q naughts being swapped out for P hat, Q hat, this is the same thing, right? We have a P times a Q divided by N. We take the square root, right? And so that's still going to be the standard error of this hypothesized population, and that's the difference. Okay? In the confidence interval case, we didn't have a hypothesized population. We're just trying to capture this thing, right? So we didn't have any ideas about what it might be. Okay. So then here in step 2, you're going to calculate Z, right? Which really is going to say, which is really find the number of standard errors p hat is from the hypothesized proportion p naught. Once we have that standardized value, right, how many standard errors p hat is from p naught, then I can use software, I can use a table to find the probability associated with this z-score. Yeah. So without an example, we can't calculate the Z. Of course, I'm going to introduce an example and work through it with all this information. But for now, we're just introducing all the things. So step 3 is going to be find the p-value. Find the p-value. Okay. Now, it doesn't hurt to introduce what the p-value is again, right? The p-value, and because you're working online, it might be an open book and all that fun stuff, right? It might be a good idea to just have, the p-value definition on a sticky note somewhere. That's one of those things that it's not going to sink in. It's not going to sink in. You can put sticky notes up all around your house, which is how I used to study. I go to grab a cup, oh, p-value. I read it. Okay. Doesn't sink in, and then eventually it sinks in. Right? And so you have to work on your memorization. Right? Mostly because just relying on understanding the concepts is a little bit tough in this case. So what is the p-value? The p-value is the probability, so the area under the curve, right? The probability. I'll put in light blue, I'll put just some clarification that's not technically part of the definition. So the probability or area under the curve, right? It's the probability of seeing something as extreme or more extreme. Of seeing something as extreme or more extreme. Oops. Than what we saw, right? And this is generic because right now we're talking about, okay, the probability of seeing a p hat as extreme or more extreme, right? And so in our scenario, a p hat, and maybe I'll say a p hat as extreme or more extreme, but that something is going to change, right, for each type of question. Okay? So it's the probability of seeing a p hat as extreme or more extreme than what we saw. And then we already established that, okay, well, this is assuming that the null hypothesis is true. So that's the end part of this definition. Assuming the null hypothesis is true. Good. So assuming, which means assuming, in our case, the sample proportion came from a population centered on P naught, right? Because our null hypothesis is that P is equal to P naught. Assuming the sample proportion came from a population centered on P naught, right? Since the null hypothesis is that P is equal to P naught, right? We have to assume that that's true until we have proof otherwise. Just check the time here. Got a lot to say. Okay, so then that's good. We know how to find this probability. It's the area under the curve, right? And so we can use software, the Z table, or what I want to introduce is using the T table, right? Or the T table to find the probability. Or maybe I'll start calling it the p-value. Now, for us, it doesn't really matter which one you want to use, but I'm going to start to focus on using the t-table. Now, the method to my madness here is, well, we just saw a little glimpse of having to calculate a t, which means that we have to use the t-table. So it's nice to have the same method in place for all of these p-values. So that's why I'm going to start to gravitate towards using the t-table. But in the beginning, we're going to confirm with the z-table, which we've used before. And then in the lab, you're going to confirm it with software, right? So Excel or whatever. So I'm going to focus. I will use the t-table mainly. Now, because you're working online, strictly online, you have to be able to use whatever the question asks you to use. And so the majority of these questions will say, using the t-table, do this. Okay. And so that's why I want to use the t-table. But I'll show you how to use the z-table, and then you can decide for yourself. Okay. We're not ready for this remember when, mostly because I don't know when that was supposed to happen. We haven't introduced that, so that's weird. Step 3, I've already given it away. There's only 4 steps. So, home stretch. All right, what could step 4 possibly be? Probably a conclusion, right? How do I use this p-value? How do I use this probability? Okay, now, kind of cheeky of me, because step 4 has 3 parts. And so that's rude, right? But it's just how it is. Step 4 is the conclusion. The conclusion, just to highlight, has 3 parts. Going back to that example, if something, if we want to say that something is unlikely to have happened under the null hypothesized proportion, then that p-value is going to be small, right? And so in general, what we're going to do is we're going to say, well, if a p-value is small enough, that's tough, right? We need to have some threshold smaller than this, right? And so so that's what we're going to introduce. But if the p-value is small enough, then we have enough evidence to reject H naught. If I'm rejecting H naught, then it's probably in favor of HA. That's kind of the flip side of my null hypothesis, right? And so then I have enough evidence to reject H naught in favor of HA. One of the key things is you're always going to state your conclusion in terms of H naught. You either have enough evidence to reject H naught or you do not. Okay, so there are only two ways that you can formulate this. And so there are only two options for the conclusions. I'm gonna write them as one sentence just so it's not so you have to link them up later, but we can separate them if you'd like. So if the p-value is less than the alpha level, more Greek. So if the p-value is less than okay, fine. I'll do them separately first because this one's the more important one. So if the p-value is less than the alpha level, now the alpha level alpha level is the significance level, and the default is 0.05. Okay, so if the p-value is less than 0.05, usually as a default, the question will say use a significance level of 0.1, use a significance level of 0.01, right? Depending on how sure you want to be. Okay, but we'll, again, more rules for later. Okay, but for now, let's just read it as 0.05. Okay, so if the p-value is less than 0.05, what does that mean? It means the probability of seeing something as extreme or more extreme is less than 5%, right? 0.05. And so what does that gives me evidence against H naught. Okay? And so if the p-value is less than the alpha level, we have enough evidence to reject H naught. Okay, it's very important that you formulate it as you either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. Why is that so important? It's so important because we assumed that the null hypothesis was true. Our whole testing scenario, we assumed that it was true, and so that's why your conclusion has to be in terms of H naught. So if the p-value is less than the alpha level, we have enough evidence to reject H naught. Now, if you're going to reject it, you should probably say in favor of what? So in favor of HA. Okay. And then what does that mean in terms of the question? That's the part of the conclusion that everyone loves to forget because you've done so much work up until this point that you can't even imagine answering the question, the original question. And so then you have to state the conclusion in terms of the question. And then, so I'll add it here, conclusion in terms of the question. Right? What does it mean to reject H naught in favor of HA in terms of the question? Okay. So in terms of, I said that the conclusion has three parts. Okay? The first part of the conclusion, so the conclusion has three parts. The first part of the conclusion, uh-oh, I used a one with a circle here. I'll have to kind of, I don't know. Too many things. So the first part of the conclusion is you compare the p-value to the alpha level. Now it is either less than the alpha level or more than the alpha level. It's never going to be exactly the alpha level, so that's not a concern, right? But the p-value is either less than the alpha level or greater than the alpha level. Or, as I prefer it, not less than the alpha level, right? To really simplify things. And so the first part of the conclusion is where you say what your p-value is and if it's less than or not less than the alpha level. So compare the p-value to the alpha level. Then the second part of the conclusion is what does that mean? What's your conclusion in terms of H naught? So 2 is your conclusion in terms of H naught. Do you have enough evidence to reject H naught or not? Right? And then, okay, fine, I'll use pink. The last part, arguably the most important that people love to forget, is the conclusion in terms of the question. Oops. Now, okay, good. So there are two options for the conclusion, and those two options each have three parts, of course. And to emphasize how similar these options are, it's just whether the p-value is less than the alpha level or not. I'm going to copy this option 1, and then I'm going to strike out the changes and just kind of edit it that way. Have you ever thought about saying I edited it? I edited it. Anyways, things I think about. I edited it. Maybe it's just me, I just can't say it. Maybe. You know what? I'm going to keep that circle there. And I'll just put 0.05 here. Just briefly. Okay. And then in red, I'm going to edit it. I'm going to edit it. Edit it. Here's my second option. If the p-value is not less than the alpha level, then what? Then we do not have enough evidence to reject H naught. Now, if you're not going to reject it, then this part's out, right? It's technically not incorrect to say we do not have enough evidence to reject H naught in favor of HA. I just think it sounds a little bit weird and a little bit misleading, and so I like to just period, right? And that's the only change. You could technically apply this entire sentence over again, but so now you do not have enough evidence to reject H naught. And of course, the same follow-up. What does that mean in terms of the question? Right? And so there's really only very few changes here, as long as you keep the sentence structure, right? You compare the p-value. Is it less than the alpha level or is it not less than the alpha level? You either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. And then, of course, what does that mean in terms of the question? Okay, let me check the... Oh, time flies when you're having fun. Yeah. Okay, let's see here. Think fast, Emily. What are you gonna do? Let's get the types of errors out of the way. So I'm not gonna, we won't have time to do an example. We'll do it, we'll pick up on Thursday, but I want you to try to pick it apart and try to figure it out before Wednesday. But before that, if I'm setting my alpha level to be 0.05, I'm okay with being wrong 5% of the time. So what does that, how can we talk about those errors? Now, if I reject H naught because my sample told me so, there's a chance that I'm wrong, right? So we have to talk about those errors. Now, this is going to be like a little, it does, yeah. So the question was, do both conclusion options, right, use all three parts? And it does. It's just the change here. So you still have to compare the p-value to the alpha level. Haha. You still have to state your conclusion in terms of H naught and your conclusion in terms of the question. But there's always a chance that we're wrong. We don't know if we're right or wrong. We say the probability is low, right, that we're wrong, but there's always a chance that we're wrong. So what I want to do is I'm just going to put a little X on the slides that we didn't do, right? But you can review these on your own. I don't really like, so this, I don't know when that would have happened. It's just introducing a new example, but it's just walking you through hypothesis testing in general. And so it's nice to kind of have this overview, but it's basically what we did when I just wrote everything out. And so here, blah, blah, blah. These are nice. You can review these on your own. And so here, I want to just briefly talk about decision errors. Okay. So we might be making a mistake. Okay. What are some mistakes that I could be making? I could reject H naught when it shouldn't be rejected, or I could fail to reject H naught when I should have rejected it. And so those are my two options, my two types of errors. And so to summarize these errors, we have the decision that we made and some truth that unknown truth. Okay. And so it exists, right? Just like the population proportion exists, but we don't know it, right? And so this is some unknown truth, and this is what we decided. So I decided to fail to reject H naught. Well, if H naught is true, then that's fine. That's not an error. But if I fail to reject H naught, so I don't have enough evidence to reject H naught, when HA is actually true, when the alternative is true, that's what we call a type 2 error. Okay? The one that we're more concerned with is a type 1 error, when I've rejected H naught when it should not be rejected. Okay? And so, so here, a type 1 error is the one that we're going to be most concerned with. Okay, type 2 error is really hard to avoid. We're just kind of we're not as concerned right? I said that there's no difference, but oh, turns out there was a difference. Oh well. And so if we think about these errors in terms of a trial or a criminal trial, then the null hypothesis is that you're assumed innocent until you're proven guilty, right? And so the alternative is that you're guilty. Okay? And so now, if I say, well, I'm going to say that the defendant is innocent when they're actually guilty, so I failed to reject H naught when the alternative was true, well, that feels like I failed to reject H naught when the alternative was true, making this a type 2 error. And I've got the answers on the next slide, so I'll just talk about them here. What if I say, okay, the defendant is guilty, which means I rejected H naught in favor of HA when they're actually innocent, when I shouldn't have rejected H naught. And so if I go back here, I rejected H naught when I shouldn't have, that's a type 1 error. That's worse, right? Arguably worse to say that the defendant is guilty when they're actually innocent, right? We tend to err on the side of, okay, if I had to make a wrong decision here, I guess I would say that this defendant is innocent when they're actually guilty rather than the other way around, right? And so that's the same approach that we have for hypothesis testing. Okay. So let me see here. Uh-oh, I'm out of time. Okay, so the significance level is the alpha level. Okay, I just want to jot that down. Alpha level. You can write alpha or use the fish. Okay? But that's how comfortable we are with making a type 1 error. And with that, I'll leave you until Thursday. But the example that I want you to try for Thursday. Huh? So you can try this example, pick away at it, think about hypothesis testing, and then that's where we'll pick up on Thursday. If you have any questions, let me know. Otherwise, I'll see you then. I'll stop this recording.